Okay, being recorded. Okay, Valentin, thank you very much for accepting our invitation for our seminar. We have here Valentin to speak about, well, there is no largest proper operator ideal. Go ahead, you have the space.
Thanks a lot. Thanks, Bruno, for the invitation. Okay, so I'm going to talk about this problem, this solution to a problem of Pietsch. Actually, I've already have given previous talks about this, but there are some new informations here for those who attended the previous one. So, okay, I will start with a bit of background, introduce a new class of proper ideals which answer the questions, and I would like to be able to spend a bit of time on more details on the proof. So first of all, we have the notion of operator ideals in the sense of Pietsch. So this is abstract definition, just of course, I mean, think of the compact operators, for example. So what is in general an operator ideal U? It's a collection of subspaces of any of the space of operators between any pair of Banach spaces. So for any pair of Banach spaces X and Y, you have a subspace which has to be an ideal in the following sense. Well, first of all, it has to be non-trivial, so it contains the finite rank operators. And then the second part here is that you want to have the ideal property, but you want to be able to compose on the left and on the right by any operator going from possibly from between any pair of Banach spaces, and you require this condition whenever the composition makes sense, right? So so in particular, of course, if you fix if you look at U of X, which is U of X, it's a two-sided ideal of L of X in the usual sense, but you require more. You want to define what it means to be the ideal also for an operator from X, Y. And so you cannot just choose freely any ideal for any, I mean, you cannot make any choice of ideal for any X and then hope to join them together in an operator ideal. I mean, if you fix, for example, that you will choose the compact operators on L2, then this will impose some conditions on what the ideal will be if you look on LP or C0 or other spaces. So, yeah, okay. Well, of course, please interrupt me if you have any questions during the talk. Classical operator ideals, there are many, but the one we will be interested in, I mean, our main ideal of interest will be the ideal of inessential operators. I will talk about this in a minute. First of all, of course, we have the finite rank operators between Banach spaces, compact operators, strictly singular operators, which means that no restriction of S of such an operator to an infinite dimensional subspace can be an isomorphism onto the image, but we won't need to work with them exactly. And of course, the point of working with operator ideals is that all these ideals are different. If we were just looking at operators on the Hilbert space, then the only closed non-trivial two-sided ideal is the compact, the ideal of compact, and so we would not see this difference on the Hilbert space. This is the same if we were looking at little LP. Already looking at classical spaces, if you look at capital LP, then you have already many different ideals. But here we can, I mean, to differentiate them, we can pick a convenient pair of Banach spaces and find a difference there. So let me quickly comment. Of course, I mean, the fact that there are compact operators which are not in the closure of finite rank operators, that's not trivial at all. That's comes from work of N-Flow on the approximation property. Strictly singular, which is not compact, that's easy to find between LP spaces. Inessential, which is not strictly singular, well, maybe let me first give the definition of an inessential operator. It was first defined by Kleinecke on a fixed space, and then by Pietsch extending to the case of an operator between two different spaces. Well, first of all, let us look maybe at the case of when there exist Fredholm operators between x and y. So say typically assume that x is equal to y, then being inessential is the same as preserving the class of Fredholm operators. So what is a Fredholm operator? It's something which induces an isomorphism between finite codimensional subspaces of x. So it is an isomorphism between the two spaces up to finite dimensional perturbation if you want. So that's an inessential operator on the space X, and then Pietsch was able to extend this definition to this case so that it becomes an operator ideal. And then, well, to do that, you have to use this definition when you do a composition here to be able to talk about perturbation of the identity, and this works well. And actually, well, there are some abstract reasons to define something inessential like that, but let me skip this. So a point that I want to make, I don't know of a very classical space where you can see the difference between these two ideals. The only space that I know, I mean, the less exotic space that I know where you can find this is the so-called Carlton-Peck space, in which case you have a certain, so Carlton-Peck space is a space which contains a copy of the Hilbert space, which is inserted in Z2 in a very exotic way, so that this embedding of L2 in Z2 is, although it is an isomorphism, of course, it is an embedding, is not, it is an essential. Well, anyway, this is not the main point of my talk, so let me skip to what follows. So what is a proper operator ideal? So Pietsch defined a class. It could be an ideal or not be an ideal. So if it's not an ideal, we think of a class as we define operator ideals, a class of subsets of L of x, y for any pair of Banach spaces x and y. It is proper if whenever the identity of x belongs to you only when x is finite dimensional. Of course, if x is finite dimensional, then the identity of x as finite ranks will belong to you, but this is an equivalence. In other words, it means that it is proper if whenever x is relevant, meaning infinite dimensional, then u of x is a proper ideal of L of x. So that justifies the name. So of course, the previous ideals are proper. It's not difficult to see for inessential operators as well. And okay. So we don't know, I mean, a proper ideal, it has to be proper if you restrict to any x. And now if you look at what happens for you between two spaces x and y, then it's there is no condition. This has two questions. First of all, is the ideal of inessential operators the largest proper operator ideal? This is motivated by the fact that if I go back to definition, it is obvious that the being a proper ideal is hereditary. A sub-ideal of a proper ideal is again proper because, well, if it belongs to you, then it belongs to a sub-ideal if the identity belongs to a sub-ideal, then it has to belong to you, so that's obvious. So once you know that this that being proper is hereditary, it is natural to ask if there is a largest one, something universal, like being proper would be the same as being a sub-ideal of this largest one, right? And there are some apart from the fact that there were no other candidates, there were some abstract reasons also to assume that this was a natural candidate. But let me skip this because the answer is negative, as I will comment here. And of course, then the second question is, if it were, if it is not the largest proper operator ideal, then well, does there exist one? Okay, and so the answer is negative, but in two different ways. So first of all, if you are looking at inessential operators, it's not even maximal. So I will show how to construct another proper ideal, which is strictly bigger. And this new one will not be the largest one, because there is no largest one, because just by using a technical modification of this example, we will be able to construct two proper ideals strictly bigger than this one, in such a way as the sum, which is again an ideal, is not proper. So so you see, because of this, there cannot be a largest proper ideal, because this hypothetical largest proper operator ideal would contain these two ones. So it would have to contain the sum, which would have to be proper by the fact that proper is hereditary, so we would get a contradiction. We benefited a lot from previous work from Aiena-González and Gowers-Maurey, as well as conversation with González and Antonio Martinez d'Abejon. Okay. So now I will start. What I'm going to do is try to give an idea of this theorem here. So first of all, I will focus on the first aspect. So I will be looking at inessential operators. We will maybe find this V, and then we will see how we can modify V to get these two versions here. So let us first try to understand what is going on with this situation here. So that's Aiena-González's approach. They were investigating this question, and their approach was to consider so-called improjective operators. The definition is due to Taravda in 1972. An operator is projective if it induces an isomorphism between infinite dimensional complemented subspaces of X and Y respectively, and improjective otherwise. Okay, so one obvious case would be if the complement, well, first of all, if T is an isomorphism between infinite dimensional spaces, then it is projective. Or if it is Fredholm, it means if the complemented subspaces you are looking at are just finite codimensional, which are always complemented, then it will be projective as well. So what I noted here is that Fredholm operators between infinite dimensional spaces are projective. So an improjective operator cannot be Fredholm. It's not very difficult to prove that the class of improjective operators is proper. Well, because why is that? Well, if the identity of X belongs to imp, so then the identity of X, of course, is projective if X is infinite dimensional. So that is only possible if X is finite dimensional, so that's immediate. And it's also classical and not difficult to show that we have the inclusion of this inclusion here. So any inessential operator is improjective. And actually, it's also not too difficult to show that if U is an ideal, then U is proper if and only if it is included in the in-projective operators. So let us have a look at this equivalence here. Of course, that suggests two things, and that's what Aiena and González were investigating. Well, it would be nice if actually those two classes were the same. Then, of course, we would solve the question, and in this case, inessential operators would form the largest proper ideal. Secondly, well, maybe if they were different, when at least we could hope that this class of operators would be an ideal, and then, of course, it would be the largest proper ideal. Well, you can imagine that they did not manage to prove this. Actually, they proved that this is not true. So so let me anticipate here. Well, they prove that these two classes are different. So let us first have a look. Then we will afterwards we will look at this question of the ideal here. So what they were trying to do is trying to show that these classes are different. So they want to construct, because of this inclusion here, they want to construct something which is improjective but essential. So when they were working on this question, it was shortly after the construction by Gowers-Maurey of exotic spaces, such as the famous hereditary Intercomposible space. So let me not enter too much in the definition here, but the point is that such spaces have very few operators. Actually, it's usually said that have few operators, because after that, other spaces, even more exotic, were said to have very few operators. But so there, any operator is either Fredon, so it is actually a perturbation of an isomorphism, or it is strictly singular. Because of this, it is immediate to see that you will not be able to differentiate these classes. And so, even though it seems to be a good idea to work with exotic spaces because we have a nice characterization of, I mean, it's very rigid, so it's a help to solve this kind of questions. This particular type of space is too rigid to obtain this. But then they turn to another example, which is an indecomposable space. So what is an indecomposable space? It's a space which does not admit any non-trivial complemented subspace. So if you look at a complemented subspace of X, it has to be either finite dimensional or a finite codimension, in which case it is obviously complemented. Or in terms of projection, the only projections are the finite rank ones or the one of cofinite rank. So requiring to be indecomposable is still exotic, but less exotic than being HI. And it is equivalent to saying, I mean, yeah, I guess it is equivalent to saying that you have a decomposition of the algebra of operators between the Fredon operator and the improjective ones. Why? Well, because either you are improjective or you are projective. If you are projective, you are an isomorphism between complemented subspaces. But if the space is undecomposable, if you are projective, you are an isomorphism between complemented infinite dimensional subspaces. If the space is undecomposable, those infinite dimensional complemented subspaces have to be finite codimensional, so you are actually Fredon. So this is really a reformulation of the decomposability. And so if you wish, you can think that because of the works of Gowers-Maurey on exotic spaces, there is a space X where you have exactly this partition of L of X between these two extreme cases. So yeah, so they need such a space, and as I just said, such a space exists. And this is a formulation of the theorem of Gowers-Maurey in 1997, which enunciates the existence of such a space. So the construction is, of course, extremely complicated, but we can sum up the properties of X as follows. Well, first of all, as I said, it is indecomposable, so it is the same requiring that a subspace is complemented as saying that Y is finite codimensional. So the equivalence of these two first propositions is just saying that it is indecomposable. Furthermore, they prove that all these finite codimensional subspaces, for example, the hyperplanes, are again isomorphic to X, which is classical for Banach spaces, but not always the case for exotic Banach spaces. And moreover, if you have a subspace which is infinite codimensional, then you cannot be isomorphic to X, right? So this is very rigid in this sense. You have those copies of X which are complemented. They are the only one which are complemented, which are the finite codimensional copies. And actually, it is very rigid. It has few operators, but still, it admits at least one operator which induces an isomorphism between X and its hyperplanes, which is the right shift operator on a canonical basis of X. So you have basically on this space the right shift operator, the algebra generated by it, and nothing else apart from compact or strictly singular perturbation. So, and I will come back to this, in terms of the algebra of operators, everything up to perturbations comes from this right shift operator. Well, also the left shift, actually. Some kind of left shift. Okay, I will go back to this. But it is very important that we have this right shift operator. Okay, so maybe an idea of what they do. How do they prove? How do they construct an in-projective operator which is essential? So first of all, because this is a right shift, and as any shift on a space, on a reasonable space, maybe reflexivity or something which is not C0 or L1, but at least something which, with some regularity properties, it will behave as a right shift on L2, say, so one will be in the essential spectrum of the right shift. Actually, any element of the unit circle will be there. Here we are assuming that we are in the complex case, okay? I didn't say that, because we want to use spectral theory. So this, well, this means that one is, this means exactly that, well, this implies that this operator here is not Fredon, because otherwise one will be an eigenvalue with finite multiplicity. Here where, well, this is not the case because it is in the essential spectrum. So, so this operator S1 is improjective because so why is it improjective? Oh, well, because I said that in X, operators are either Fredon or improjective, right? But it is essential because now if you look at this operator here, which is identity of X plus R, well, since of course any element of the unit circle is in the essential spectrum, -1 is there as well, so this is also not Fredon. But the definition of it, an essential would be that the perturbation of the identity so this means that the perturbation of to the identity by S1 is not Fredon, so if it were an essential, it would have, and since the two identity is Fredon, then the perturbation here would have to be Fredon as well. Okay, so that's the example. Now, up to classical perturbation arguments, we shall replace S1 by T1, where we can assume that the image of T1 is some subspace of X of infinite codimension. Perfect. So if I just go back a few slides, they managed to prove that this inclusion here is strict. Okay, so then maybe at least imp is an ideal, but then, as I wrote here, this does not occur. So if it were an ideal, then they would have solved the problem. But just the next page, they already observed that the class of in-projective operator is not an ideal, and actually, the problem is not about composition. The problem is about being a linear subspace of L of X. So at this point, it seemed that they were stuck, but then the next step is start from where they were, and maybe we can think that this was too big. Well, actually, well, of course, I mean, if you wanted to become an ideal, you could increase it or shrink it. Okay, so here we shrink it to make it an ideal. Since we are shrinking it, so we shrink it to something called U1. Since it is included there, it is still proper. So at least we keep the proper part of the story. But by shrinking it, we manage to make it an ideal. And still, so if I go back to this T1 or S1, but I shifted it to T1, which is the operator which proves that these two classes are different. So we want still to be able to use it. So of course, we want to shrink into U1, but still keep T1 inside it. The next step is just to take the sum of these two things. T1 will be there. It's not very difficult to show that since U1 is proper, then V1 will also be proper. It is an ideal. So we obtained the first part of the story. We were able to build something which is an ideal, which is strictly bigger than this ideal here, and is proper. Okay. So here, maybe this is a moment to stop 2 minutes, because I wanted to do a drawing and maybe I could answer some questions. So my idea here was to, let me see, to stop presenting the slide. So let me try this. Now, I will try to okay, now I have my A4 paper here. And okay, so can you see this thing here? This white, okay. So summing up, what have I been doing? So here's my hand. I mean, it's not my face yet, but so first of all, we had this ideal of inessential operators. Then we had this, we had the in-projective, and we discovered that they are not an ideal. So because they are not a somewhere they're not a subspace. So, but those things are homogeneous, I see. So I will represent the fact that it's not a subspace by drawing something which is not convex, right? So that's imp. And I was able to isolate some T1 and some, oh, okay, no, so I was able to isolate some T1, which was there. And then what did I say? Well, I will be, I shrunk in-projective operator to something which, well, I want to think of this something as something convex. Maybe we have a problem. No, okay. So well, let's just assume that this red thing here is convex. That's my V1. So now that's an ideal. It is strictly bigger than inessential, and it is proper because it is contained in this in-projective thing. Now, when Aiena-González proved that this class is not an ideal, what they did was construct these two versions. So that's T1 and T minus 1, right? 1 was associated to lambda equals to 1, and minus 1 would be associated to lambda equals to minus 1. The same kind of some construction by choosing, using that minus 1 is in the essential spectrum instead of 1. And then, of course, you can do exactly the same construction. Oh, well, first of all, these are the two operators which indicate that you have a lack of, that it is not an ideal, because the middle point, if you want, here is not inessential, because it is something like the identity. Hold on, I just lost. Okay. And then you can define this thing here, V minus 1. So you could have done this construction that I just did with V1, also with V minus 1. Now, the sum of these two things, of these two ideals will will not be included in projective operators. So now there is a last, since I don't want to go back and forth between the slides and this nice drawing, let me just comment something, because now I will enter in a bit of more details here. So what happens is that there will be a first version of V1 which maybe will not be convex and be an ideal. So this shrinking thing here, we start with shrinking and then I will have to increase it again. So, okay, there is a step here. Maybe it's not necessary to say more. So, but the final picture will be this one, right? So just with V1, we see that inessential operators is not maximal. And with these two things, then we find these two proper ideals whose sum is not proper, implying that there is no universal proper ideal. Okay. Is there
Sorry, I didn't understand. I didn't understand what you did there in the very end. What was the point of decreasing V1 and V minus 1? I know you weren't clear, but what is it?
Yeah, sorry. So I'm just anticipating a bit. Actually, I will define the first version of V1 and V minus 1, which will be smaller. And then I will have to increase it to get something which is an ideal. So, but I haven't said what are these V1 and V minus 1 yet. So I'm not decreasing. I'm just saying that I will have a first version which I will not be sure that it will work, and then I will have to increase it a bit to be sure that it works. But okay.
Okay, thank you.
Okay, so now let me first of all go back to myself here, and then try to go back to the this here up, and okay. How is it on your side? Can you see the slide?
No, I cannot.
Ah, okay.
Yeah, now they are back.
It's back.
Okay. And now, and is it full screen or full enough?
Yeah, it's full screen now.
Okay. So again, so this is I haven't said what is V1 yet, right? I'm saying that I will have to find this V1, which will be defined from U1, which I will have to find. And that's V1 from my drawing was enough to this. And now to get this part, and then what I try to explain with the drawing, and which is stated here, is this story about using two versions, V1, or if you would, first of all, U1 and the minus 1 version. So as I said, there is nothing special about lambda equals to 1. We can use it for any complex of modulus 1. So also T minus 1 is improjective. And then if you look at the sum of these two, so recall that T1 was, okay, so T1 or S1 are essentially the same. S1 is identity of x minus r, S minus 1 identity of x plus r. The sum is 2 times identity plus some perturbation. That's what is here. Of course, this is not improjective because it is an isomorphism. And that's how they deduce imp of x is not an ideal. So as I try to draw on the paper, in the end, we find two versions of a proper ideal, which containing each of them T1 and T minus 1. The sum of the two ideals will contain the sum of T1 and T minus 1, which is essentially identity. And so since X, of course, is infinite dimensional, this ideal here is not proper. It contains the identity of some infinite dimensional space. And so, in particular, there is no largest proper ideal. Okay? So that's the main ideal. So now, what I need to do is to try to give an idea of how we define these ideals, say U1. So just to remember, it has to be still improjective, containing this T1, but become an ideal because improjective was not an ideal. Okay, so summing up, we have this strange operator T1, which was something that has to do with a shift identity minus a shift, and we want to find a proper ideal which contains, say, T1. So the first idea is to use this usual class, a class of operators factorizing or factoring through X, given X a Banach space. So an operator which you can, an operator between two spaces which you can write as, you can write a diagram where you write it as a composition of an operator in such a way that you go through this X, right? So B would go from Y to X and A from X to Z if T is defined from Y to Z. Well, this is an ideal as soon as, for example, X is isomorphic to E squared, because obviously if if AB witnesses that T belongs to op of X and A prime B prime for T prime, then you can write T plus T prime in this way, and this factorizes through X squared, whereas if X squared is isomorphic to X, then you are done. But, well, obviously this is never proper if X is infinite dimensional. That's not a good, well, the identity of X belongs there, but it's a starting point to define new ideals. And so the idea is to look at the intersection of two such ideals. So it will be an ideal. And if you use X and X prime, which are sufficiently different from each other, namely that no infinite dimensional complemented subspace of X is isomorphic to a complemented subspace of X prime, then this class will be proper. Well, because saying the identity of some space Z belongs to op of X is saying that it factorizes in this form by definition, and it's so it's equal to A times B, where F goes from X to Z and from Z to X. But since this is the identity, this is easily equivalent to saying that Z embeds by B as a subspace of X, which is complemented by BA inside X. So the identity of Z belongs to op of X if Z is complemented X. It will belong to this intersection if Z is complemented in both X and X prime. Therefore, therefore this, right? Proper means that no such Z exists. So this is exactly this condition. So now if you go back to the property of the Gowers-Maurey space, I was saying if you pick X to be this Gowers-Maurey space and X prime to be Y1, which is just some infinite codimensional subspace of X, then this will happen, right? Because what is an infinite dimensional complement subspace of X? It is something isomorphic to X. What is a complementary subspace of Y1? Well, it is something which is infinite codimensional in X. And in Gowers-Maurey space, it is not possible for something finite codimensional to be isomorphic to something infinite codimensional. So if you want, the properties of Gowers-Maurey are exactly what we want to know, that this class is proper as soon as Y1 is infinite codimensional. And since
so you mentioned right now, but I think I spaced out. What is it? YI?
So YI is the image of the operator T1 that we were using. So T1 was the operator which was in projective but essential, and it goes from X to Y1. So this is exactly actually what we need here. It defines on X and takes values in Y1. So of course, it factorizes through X and also factorizes through the image. And the same for -1.
Thank you.
Okay, so very nice. This is proper. This is really what that's a good candidate for V1 if I is equal to 1. The problem is that since X is not isomorphic to E squared, because Gowers-Maurey space is very exotic, we have no reason to think that these two things are ideals, and of course that the intersection is an ideal. So this is where this is what I was badly explaining on my drawing. This is the first version. Sorry, this is the first version of our answer. This is the first tentative for V1, but it doesn't work because we don't know if it is an ideal. So what we do next is, after having shrinking, now we have to enlarge. So instead of using operators which factorize through x, we have to use operators which factorize through some power of x. And then it is an ideal because if t factorizes through xn and t prime factorizes through xp, then t plus t prime factorizes through xn plus p. So then the problem we had looking at the sum of two operators factorizing disappears, right? So then we have an ideal. And so we enlarge this intersection to this intersection. So now it becomes an ideal, but we are hoping that it is still proper because certainly it still contains T1. Here it should have been Yi. So. And indeed, we are able to prove that not only that this larger ideal is still proper when Y is infinite codimensional in X. This comes from the following technical results. If Y is infinite codimensional in Gowers-Maurey space, then no infinite dimensional complemented subspace Z of x to the power n can embed complementarily into y to the power n. So if you remove what is in red here, this is what was known from Gowers-Maurey article, and this is what is sufficient to know that the first version of the we considered would be proper, but we didn't know it's an ideal. And once we use this enlargement here, then we need this theorem. And that's the technical part. It's not, it requires a lot of work, but a lot of things were already in Gowers-Maurey paper. And so on one hand, it is difficult because it's a lot of techniques. On the other hand, the space already existed and we did not need to define a new space. So maybe, I don't know, do I have 5 minutes maybe, or 4?
Sure, go for it.
Okay, so maybe I just want to say a word about what kind of techniques we are using here. And I should say I did not invent anything here. Everything was already, I mean, everything I needed was already in Gowers-Maurey paper. I didn't have to be extremely creative just to understand the techniques. And luckily, I mean, for me, it was nice because this was actually a paper that I looked at when I was doing my PhD in 90, well, at that time, 94, something like that. Okay. Okay, that's a final question. So maybe let me just give an idea of the proof of theorem. So first of all, we prove that an infinite dimensional complemented subspace of Xm is some power of X, and that's the first step. And then the second step is to show that, so without loss of generality, it all boils down to looking at X, and then we prove that X does not embed in Yn, but I want to insist here on one. And well, I don't have time, so let me see. This is going to be too much. The point is that Gowers and Maurey were using K theory here because essentially up to perturbation, the algebra of operator can be studied through some subalgebra of operators, which is actually isomorphic as an algebra to the linear algebra of continuous function with absolutely summable Fourier series. And so it all boils down to studying this algebra. And well, if you are looking at complemented subspaces, of course, you are looking at idempotence on this algebra, or on matrix algebras of this linear algebra. And the point is that while the case of one dimension was fairly easy, when you go to higher dimensions, you really have to use a bit more of K-theory, although certainly very classical for people who work in that. And so, through K-theory, you obtain some similarity. I mean, well, summing up, you obtain some similarity inside the matrix algebra of T, which can be lifted back to the algebra of operators on the power of X. And what was difficult for me as someone working in Banach space theory was working with the linear algebra instead of the algebra of continuous function of the torus. And okay, so that's essentially this was going to give the same thing in terms of K-theory was not so obvious to me, and but maybe obvious to people in K-theory, the notion of local Banach algebra. But okay, well, just maybe to summing up, saying that any complemented subspace of Xn is a power of X, in the end boils down to saying that any complemented subspaces of Rn is some Rn, if you want. That's the kind of magic that K-theory will do in this context. Sorry, this is vague. I just want to conclude with a question. You can generalize the question of Pietsch. A space ideal is a class of Banach spaces which contains finite dimensional ones, stable by taking direct sum and by complemented embeddings. So part for the finite rank, for the finite dimensional spaces, which we actually just considered here, you could look at Hilbertian spaces, reflexive, separable. The space of U, by definition, is this class of spaces for which the identity of X belongs to U for any ideal U. So in particular, space of okay, so if you take a space ideal, the finite dimensional spaces, then we are exactly investigating space of F, which were the I mean, what were we doing exactly? So, yeah, if you take A to be finite dimensional spaces, saying that the space of U is equal to F is exactly saying that U is proper. So we were investigating whether there was a maximal, a greater ideal for this here. So he was asking more generally if whenever you have such a space ideal, whether it can always be written as space of U for some largest ideal U. Okay, so we just proved that the answer is no for A equals to F, which is exactly then the case looking at largest proper ideal. But it's not too difficult to show that, to use our techniques to deal with other cases. And the interesting thing is that, let me skip this, but for example, we can prove that there is no largest ideal for which the space of U is the class of Hilbertian spaces. And this works as soon as you work with the space ideal whose elements are different enough from X, which was Gowers-Maurey space. So for example, since Gowers-Maurey space is reflexive and separable, those cases remain open. Maybe they could be solved by finding a non-reflexive version of Gowers-Maurey space or a non-separable version of Gowers-Maurey space. Okay. Sorry, I was in a bit of a rush for this ending. So thanks a lot for your attention here. I'm going to the bibliography, and thanks a lot.
Thank you. Thanks, Valentin. Do you have any questions for Valentin?
Valentin.
Hey.
From my couch.
Still on your couch.
I got books behind me. Okay. I don't look as comfortable as David, though. There's no question that David's the most comfortable. Nice talk. Thank you. I had a question. Let's see. Two questions. So the first is, you were talking about, maybe I don't completely understand it, but the weakly compact operators aren't the maximal ideal for the reflexive, like, okay, so you're looking at space of U.
Mm-hmm.
Could be the reflexive spaces, right?
Yeah, but you want
an ideal that would be, could you try to, I didn't quite understand completely.
So this, in this case, okay. Yeah, that's a good question, actually. So let me think. Okay, so you want that the class, the point is that if weakly, I mean the space ideal of the space ideal of the ideal of weakly compact operators will be the class of reflexive spaces.
Right.
That's true. But is it the largest one possible? Couldn't you enlarge the ideal of weakly compact operators to something for which still the identity of X belongs there only if X is reflexive?
Is it okay? So it's not obvious that there could potentially be another operator ideal, so that space of that operator are the reflexive spaces.
Yeah, and it could be. I mean, operator ideals it's restricted, right? I mean, it's not something you can see just at looking at one space, because it's something global, looking at between every pair of spaces. So it's not obvious to me. I mean, right? I mean, that's the point. You could possibly enlarge, and because you could. Maybe you could have a space which is not. You could have an operator which is not weakly compact, but I mean, you could put proper ideals there, right? I mean, you could. Take the sum of of the ideal of compact operators and then put some proper operators there, which maybe are not weakly compact. Those proper operators, the only way the identity of X belongs there, if X is finite dimensional, then reflexive, So it seems, I mean, this is just in my hands, that it's possible to enlarge, putting some things, some proper ideals which maybe contain things which are not weakly compact. So it seems possible to, yeah.
Okay.
See, I mean,
I hadn't. Okay, that makes sense. Okay, that clarifies that. I did have another question. So again, I don't know if this is, you're trying to show that you showed that there's no maximum proper ideal by showing that there's sort of two.
No greatest, right? Because no greatest.
Sorry, yeah. So no greatest. So, is there a maximal proper ideal?
Yeah, that's a good question. I don't know. So, yeah, so we are able to find something a bit bigger than inessential, and this thing which is a bit bigger, we don't know if it is maximal or not, but it's a very non-natural ideal, right? It is the sum of inessential operators and those which factor through any power of x of Gowers-Maurey space and any power of a well-chosen infinite codimensional subspace of x. So I mean,
right.
Yeah,
right.
Is it maximal? Well, okay, maybe, but it's not something you're going to use in any other.
Yeah, it's not a
pair of spaces
and desire. Okay. All right. Thank you. I'm good.
Thank you. Yeah.
Ben wants to ask something. Okay.
You said that there's no largest proper ideal, but could there be maximal proper ideals?
Yeah, so I guess that's what Kevin asked. I don't know. I see no reason why not, and I see no theoretical reason to claim that there should be, because even Zorn's lemma, I don't know how that would work, since we are, I mean, the class of Banach spaces is not a set. So, I mean, once you want to work with any pair of Banach spaces, I mean, what are you going to do? If you fix a Banach space and you look at ideals there, then probably you can say something about maximality by like this kind of set theory arguments. Then when you want to go to the general situation, I don't know. So it seems pretty open to me.
And what about just instead of fixing a Banach space, just fixing some density character then, so you can code it inside of something else?
Yeah, you're right. Okay, so maybe just for separable, I guess, but so you would have probably a maximal proper ideal for the definition of proper restricted to separable spaces or whatever density you want to fix.
And do we have other questions? Okay, if there are no more questions, I will then stop the recording.